Let's start off this lesson by going over our two commandments of mathematical domain, and that is thou shalt not divide by zero, and thou shalt not take a square root or any even root of a negative number. So you can actually see this in your calculator. If I put in my calculator 7 divided by 0, it's going to give you an error because you divided by 0. So it does not like that. You cannot do it. Also, taking the square root of a negative number. So if I do the square root of 4, we get 2. But if I do the square root of -4, you're going to get another error. We have a non-real answer here. And we'll find out later that when I have a negative under a radical, that becomes an imaginary answer. So it is not a real number. We get imaginary numbers. Now, the main thing for this lesson and really this class is taking square roots, but I want to make it sure it's known going in future classes and stuff that works for any even root. So if you do the 4th root, 6th root, 8th root, 10th root, so on, you can't have a negative under the radical. If your index is a odd number, so if you take the cubic root, the 5th root, 7th root, so on, you can have a negative number under that radical. You just cannot for even roots. So let's use this information to find the domain. Now, you can use your calculator and graph this, but it's quicker to just find the domain using these two commandments. If I have a fraction here, I need to worry about dividing by 0. So I'm going to take what's in the denominator, and it cannot equal 0. So we're going to add that 7 over, and we get that x cannot equal 7. Now, depending on the question, you're going to have to write this in two different forms, in set notation and interval notation. So in set notation, this is this is the set of all x such that x cannot equal 7. An interval notation, and let me flip back here real quick. When I go back to lesson 3, when we went over this graph here, when we have a number that it can't equal, then that's the only number on this number line it cannot equal. So it can equal any number less than that number and any number greater than that number. So that means that this could equal less than negatives or less than 7 and greater than 7, just not 7. And so it skips over that 7 since both of these 7s have parentheses here. Okay, so same thing here. 2x doesn't have a denominator, so I don't need to worry about that. I just care about this denominator here. We have 5x plus 15 cannot equal 0. So solve. What are we doing? Subtract that 15 over. And divide by 5, and we get that x cannot equal -3. So in set notation, this is the set of all x such that x cannot equal -3. And interval notation, we need every number less than -3. And then the union, we need every number greater than -3. So just to be very, very clear here, because I actually don't think I said this in lesson 3, when we were writing our answer in multiple forms, set notation and interval notation are saying the exact same thing, just wrote in two different forms. Okay, just like the graph is also telling us the same thing, just a visual representation. This is just different ways to represent the exact same thing. Now, starting at C, we now start having radicals. And so because this is a square root, I cannot have a negative under it. So I'm going to take only what's under that radical, x minus 8, and set that to be greater than or equal to 0. I can have the square root of 0. That's okay. That gives me 0. It just cannot go lower than that. So add that over and we get x must be greater than or equal to 8. So in set notation, that's the set of all x such that x must be greater than or equal to 8. And then in interval notation, we need every number that is greater than 8 or equal to it. So that is bracket 8 to infinity. Same thing here on D. All I care about is what's under that radical, and I want to make sure it is positive. So we are talking about every number that is greater than or equal to 0. So solve. Subtract your 12 over. And then divide by -4. When I divide by a negative number with inequalities, we have to flip that sign. So now we get x must be less than or equal to 3. So that is the set of all x such that x is less than or equal to 3. And interval notation, we're talking about everything less than 3. So negative infinity to 3, and because it's or equals to with a bracket. Okay, two more examples on the next page. E is a lot like B in the fact that this 3x here has no radicals and also has no fraction. So I don't need to worry about dividing by 0 anywhere in this 3x or having a negative under radical. The only thing I care about is what's under this radical right here. So we have 2x plus 8 is greater than or equal to 0. Subtract your 8. And divide by 2. Because I'm dividing by a positive 2, I'm not switching that sign. And so that is the set of all x such that x must be greater than or equal to -4. Or in interval notation, we have bracket 4 to infinity. Now this one on F is a combination of both. Because it's a fraction, I know that this denominator here cannot equal 0. But I also know what's under that radical, it's got to be more than 0 or above. So now I'm going to take what's under that radical and set it to be greater than 0. I'm going to make a little note here. And I'll use a different color. That this is not greater than or equal to. Because it cannot equal 0 because it's in that denominator here. So it must be greater than 0. So subtract our 9 over and we get x is greater than -9. So now we have the set of all x such that x, I almost put or equals to, but it is not or equals to, but x is greater than -9. And in interval notation, that's now parentheses 9 to infinity.